So yes, my talk is titled The Memory Effects in Repeated Uses of Quantum Channels, the Impact on Quantum State Transfer, Entanglement Distribution, and Channel Capacity. So the topic of the work is in quantum state transfer. So to start, I'll just give a brief overview of what that is. So what is quantum state transfer? Well, loosely, the goal is to transfer a state between two locations with as little loss as possible. The field was initiated by Bose in 2003, who proposed that this could be done by connecting both locations with a spin chain, and then by initiating the first site with some pure state, the coherent dynamics of the spin chain could result in transport between one end and the other. So what was his motivation for coming up with this? Well, to quote Alistair Kay, the motivation being that in a quantum computer based on, for instance, a solid state architecture, interactions are typically local, but we want to apply entangling gates between distant qubits. While a sequence of swap gates suffices to bring these distant qubits together, this is potentially prone to massive control errors, and it would be desirable to remove the need for such stringent control. So what Alistair Kay is talking about here is that in, for example, a distributed quantum computing scenario, you might want to take the output of one computer and then ferry it as the input of another. And the quantum state transfer scheme that Bose proposed is, promises to do this with better fidelity than simply gates, swap gates. So to quickly go over what Bose's proposal was, if we have a chain of n spins that is initialized in the computational zero state, save for the first site that is initiated with some pure state, you then evolve the total system using some unitary and some Hamiltonian for some time t. In general, what you end up with is that once you trace out the last site, that will be in general some mixed state, and the chain qubits will be also in some mixed state. And the idea is that you have the last site be as close to the state that was sent as possible. How do we typically quantify this closeness? Well, we use the fidelity of state transfer, which is 1 when they're identical and 0 when they're totally orthogonal. So in that step, I mentioned that we need a Hamiltonian to cover the evolution. And here I just list the properties of in our work, I list the properties of the Hamiltonian that we require our Hamiltonian to have. And these properties are U1 symmetry and that it is quadratic in fermions. So U1 symmetry formally translates to commutation with a total magnetization operator. And it basically means that there's excitation conservation. So if your system has one spin up state, then it'll have one spin up state throughout the whole of the dynamics. And it being quadratic in fermions means that after you do a Jordan-Wigner transformation, the resulting Hamiltonian is quadratic in fermionic and is quadratic in fermionic creation and annihilation operators. So these are just some definitions. All right, so we have that the fidelity is how you quantify how well a specific state was transferred. But how do you qualify how well a general scheme is? And for that, the typical metric is the average fidelity, which is just the fidelity averaging over sending all pure states in the channel. And it was shown that for sending one state, that expression can be evaluated into this one up to a local phase gate applied on the last site. This is in terms of transition amplitudes, which are just the unitary expressed in the computational basis. And They just give the amplitude of transferring from one site to the other. Okay, so all of that was known stuff. Our work picks up after the chain has been used once. So, as I said, in general, we have the last site and the remainder of the chain both in a mixed state. Standard quantum state transfer schemes, they assume that these intermediary qubits between the first and last sites are in the computational zero state. And so if you want to go from this state to a computational zero state, you have to realign all the spins. So you have to pay some kind of energetic or time cost. So what we ask is how well can you do quantum information processing tasks if you don't do this resetting and just try to attach a new state on the first site and the end site and send that through the channel in this sort of dirtied state. And we want to find out how many times can a channel be reused for quantum information processing tasks. So that was the introduction. Next, I'll go over the multiple use protocol that we considered. All right, so the protocol is essentially one use of the channel, but we repeat the procedure. So we have this chain of spins connecting two sites. At time zero, we attach one qubit on one site, and then on the receiver site, we attach a zero state to act as storage for the state on the first site. We evolve that for time t1. After time t1, we disconnect the first and last sites, reconnect a second sender state and a second receiver state, and we evolve the system again for time t2, and we repeat this n times until the full register of sender states has been transmitted to the register of receiver states. So doing this, each time the state of the intermediate qubits becomes dependent on an additional set of A and B that qualified the states of the previous uses and the time of the transfers. And so then in this scheme, you can define the nth use receiver that depends on all the previous uses, and this will be sort of what you get at the other side after using this channel for n times. So now the next question would be, how do we quantify how close this state is to the state that was already sent? And how do we quantify the overall quality of this scheme? And to do that, we define the nth average use fidelity, which is similar to the first use, except that we are now integrating over each of the previous uses that came before, over all the block spheres. And so that in this way, this quantity sort of represents the global average of how well the channel is done over all of the uses. So this term can be simplified quite a bit. So if I write out here explicitly the second use average fidelity, and then I expand the state of rho R2 in terms of traces, then you'll agree that the integration, the average over the first use only acts on the state of the channel after the first use. And since sort of inner products, traces, unitary multiplications, and tensor products are all linear operations, you can sort of slide this integral in a factor of 1 on 4 pi to this state, and you can perform this average over the state, and then you can rewrite the second use average fidelity in terms of this, what I call the average channel, what we call. So by overbar, I mean the average channel. And so this you can do for any number of uses. So then in general, you can slide n-1 integrations in and evaluate them. And then, so you can have this concept of the average end-use channel. That is the average channel where you have the average channel of the previous use inside. And so using this average channel, the end average use fidelity then goes down to this kind of smaller form where it's just dependent on one integration only over the end use. So what we show is that for U1 symmetric and quadratic Hamiltonians, this expression can be simplified or evaluated to this one here, where it looks very similar to the first use, save for the presence of this term an-1, which we call the memory term. So this is the term that accounts for the fact for all the previous uses of the channel. So next I'll describe how this term is evaluated actually. So we don't have a kind of a closed form expression for it, but we have a procedure for how to evaluate this term for any n. So since it depends on all the previous uses, this procedure, it requires kind of building a sort of a tree of histories where you classify like what can happen to the channel after each use, and then you kind of expand the tree from these distinct categories. So what am I saying? So after the first use, we can sort of come up with two distinct classes where either the excitation that was on the first site ends up again on the first site or the last site after the first use, in which case when we disconnect these sites to connect the second pair of senders and receivers, the first use state is taken out of the channel and it's like an effective reset. Or we could have that the state is lost somewhere in the chain. If it's an effective reset, then nothing interesting happens. So we stick to this case where the excitation is in the chain, and we go to the second use. And then here we can talk about three different possibilities. We can have that both the first and second use states arrive on the last and the first sites by the second use. And so then by the third use, when we disconnect these two sites, we get another effective reset of the channel. We can get that one of them remains in the channel and one is effectively taken out. Or we can get that both of them are left inside the channel. And the occurrences of these outcomes depends on the two-particle amplitude, which is just the amplitude to have two excitations somewhere in the state to go to two other sites. So bearing these classes in mind, we can build this kind of tree. So here we have sort of what I talked about before. After the first use, you can have that the chain empties and then there's an effective reset, or that there's one excitation stuck in the chain. If there's one, then you can have that there's that both exit, that one is left, or that both are left, and you can continue to build this tree in this way. And in order to get the A term, what you have to do is, for the nth use, you propagate this tree n-1 times, and then you select all those paths that terminate in a zero by the final layer. And then for each of those paths, you can associate a term in this memory term that is a function of the amplitudes that you pick up along the way. So to give an example, if we imagine 3 uses, that depends on A2, then we propagate this tree down 2 layers. There are 2 paths that terminate in 0. These are the paths 0, 0, 0 and 0, 1, 0. And for these 2 paths, we then get these 2 terms that appear in A2, and A2 is then just the sum of these two terms. And there are deterministic rules of how to go from these amplitudes to the functions that then show up in the memory kernel. Okay, so now there's one final simplification that we can make to this term. So we notice in the second term, we have the appearance of a 2-particle amplitude and a summation over P1, where P1 effectively runs over the number of sites in between the first and the last. So since our Hamiltonian is quadratic, it follows that any higher order amplitude can be expressed as a function of single particle amplitudes using Slater determinants. And so using this fact, we can get rid of the 2-particle amplitude, and we then are left with this term. And with this term then, by writing out the definitions of the single particle amplitude, we can effectively, using the completeness relation, sum over these outer products of P1. And so, well, doing this then just becomes 3 terms. And all the amplitudes that are present in the memory term then become solely dependent on single particle transition amplitudes between the first and the last site. Which also means that this A term is then effectively independent of the length of the channel, because the dependence effectively was in the fact that you have to sum over all these sites. So if we get rid of that sum, there's no dependence on channel length. Inside the... Oops, sorry? Sorry? Oh, okay, yes. So it depends on the length in that the amplitude depends on the length, but no. Okay. Okay. So it still implicitly depends, but we don't have extra terms because of the. All right, so to summarize, for our repeated use protocol, we derive the following expression for the nth-use average fidelity, where the memory effects are only in this A term here. This term depends on single particle transition amplitude between the first and the last site, and only implicitly depends on the length by the presence of this n in the amplitude. And we presented a procedure for how to evaluate this term for any n. And when does it hold? It holds when the Hamiltonian governing the evolution is U1 symmetric and quadratic in its fermionic representation. All right, so results. Now we're essentially going to evaluate this term for 3 cases. We're going to look at repeated use quantum state transfer. We're going to look at repeatedly sending entangled states to see how entanglement is preserved over multiple uses. And then we're going to give some upper bounds on the quantum capacity of the channel. All right, so for n repeated uses, to evaluate it, we consider the XX Hamiltonian and the Christendal coupling scheme. So this is a perfect state transfer scheme where for time pi on 2, you get fidelity 1. And so we consider that the system is affected by a timing error. And we consider two cases. The readout time is affected by a constant shift at each use. So every use, there is a shift delta I away from this perfect transfer time. And we consider where the transfer time of the nth use is some fixed time, and then the times of the previous uses are different in general for each use and are they're drawn uniformly from an interval perfect state transfer time to 80% perfect state transfer time. All right, so first graph. So here we plot a chain of 12 sites and we consider different readout error amounts. So 0 means that there's 0% error, so it's perfect state transfer time every single use. And so of course then you get that the fidelity is 1 each time because the channel is effectively reset with every use. And then we can see that as the error amount gets larger, from 1% to 10%, with each use, you see a sort of monotonic decrease in the end use average fidelity, where the decrease gets greater the larger that the error is. And so we can see in this purple curve, for example, that if the error is more than 10%, then by the, say, 10th use or after the 10th use, in that case, the nth use average fidelity is below the LOCC limit. And at that point, it would be as good to transfer things classically. So you lose any advantage after 10 uses. But then, for example, if we look at if it's only 1 or 2%, then you maintain a a relatively high fidelity for many uses. So in this case, you could sort of get away with not resetting the channel and still have high fidelity for a number of uses. Okay, so in this plot, we now fix the error amount to 1% with each use, and we plot the nth use average fidelity with respect to n, capital N, which is the length of the channel, and then the different curves correspond to a different number of uses. So since in this scheme, as the length of the channel gets larger, the couplings kind of increase proportionally. So the transfer gets faster and as such is more sensitive to readout errors. And so, I mean, that's why in general we see that even in the case of the first use, which is the standard case, there is a gradual decrease in the average fidelity as the chain gets longer. And it also explains why then as we go up in uses, the decrease of the end use fidelity with chain length is more pronounced, showing that in this case, as the channel gets longer, it becomes more sensitive to the memory effects of repeated uses. In this inset, we then take kind of a vertical slice of the main graph and again plot the average end-use fidelity with respect to uses. And so here the main point is that, for example, even if we have a chain that is length okay, I think this legend is wrong. So this bottom line is for length 5,000. And if the chain is length 5,000, then even after a single use, the average end-use fidelity will be below a LOCC. And so in that case, you'd have to reset the channel in order to get any kind of advantage. All right, so now we move to the case where the end use time is fixed and the previous use times are allowed to vary. And so and then we plot the average end use fidelity would affect the number of uses again. And so here the main takeaway is that that memory effects are always detrimental because the average fidelity for uses after the first are always found below that of the first, but it is not necessarily monotonically detrimental because we have, for example, in the black curve, the fidelity from the second to the third case increases relative to each other. And so what this shows is that the memory term A2, that depends on T2 and T1, is not strictly less than the memory term A1, that only depends on AT1. So then here we plot similar curves to what I showed on the previous graph, but we plot thousands of them, and we change the fixed time at the end use to be 95% PST. And this is to paint a clearer picture, basically, that the effects of memory are always detrimental because for none of these curves does the average second use fidelity overtake that of the first use, which is plotted by this purple curve up there. Mm-hmm. Yeah, so in this picture, I'm plotting several of these curves, and then yeah, in this plot, there's many, just to show that nothing ever overtakes this line. Well, if you choose the times to be always perfect, then you would get, yeah, kind of. So like, yeah, this is a very difficult line to get. If you have any error, then typically you should expect that it goes down. All right, so to summarize, memory effects are always detrimental since the highest achievable fidelity is that of the memoryless case, which basically means that the A term is always between 0 and 1. Memory effects are not necessarily monotonically detrimental. That of the next use can be less impactful than that in the previous use. Memory effects can be detrimental to the point where the average transfer fidelity is below the LOCC limit. This can even occur after a single use. And the coupling strength scales with N. So these couplings make it more sensitive to the previous use's effects. And so we see, and then even in the case of repeated uses, this makes it more sensitive as the chain gets longer. Okay, so now we move on to concurrence. So just to talk about the protocol that we use for concurrence, instead of sending a state with each use, we consider sending one part of an entangled phi plus state. So then in this case, the receiver state is now given by this expression, and thankfully, we can evaluate how well the concurrence has been transferred. A lot of the heavy lifting was done for us when we walked through how to get the end-use receiver for the state transfer case. And we can get there through dynamical maps. So here I report the dynamical map for the first use, which is a sort of a known result. And we found that for the end use, the dynamical map linking the average receiver as a function of the end-use sender is given by this. So here we can see that there's the 8 n terms that I described earlier, but there's also the appearance of this b term. And thankfully, this b term is more simple to understand than the a term. So for b1, I write it explicitly here, is this summation. And this product of amplitudes, f1, j1, j1n, essentially describes a procedure where an excitation on the first site jumps to the site j1 at time after the first use, and then in the second use goes from the site j1 to site n. So that's basically all the b1 term contains. So then in general, it's given by this summation here, and it's basically just a product of amplitudes that describes jumps from the n-1 use from 1 to j1, j1 to j2, etc., etc. And then we get from j1 to n again on the nth use, and then the b term of the sum over all these amplitudes. So knowing that, we can evaluate this dynamical map. And having this dynamical map, we found that the dynamical map then, which acts on the joint entangled state at the beginning to give the joint state of the receiver and the state S tilde, is nothing but the identity tensor this nth dynamical map. So then knowing this, we can evaluate basically the state of the joint, the total state of the receiver. So then with that evaluated, we just needed a metric to sort of qualify how well the entanglement has been transferred. And for that, we use the concurrence, which for 2-qubit X-type states is just given by this expression here. So now I'll show a graph that shows plots of the concurrence, where again we take the Hamiltonian governing the evolution to be the XX Hamiltonian with crystal couplings. So yeah, so then here we again consider that each use is affected by a constant shift. And so then we plot the first to the fifth use concurrence, considering a constant shift at each use. So then, of course, for one use, it's always perfect. So it's always, you get maximal transfer. And then as you get more and more errors, the concurrence gradually decreases with each use. And you can notice that for large enough error, there is a cutoff where you get zero concurrence that is transferred through the channel. And the reason for this is that since the channel becomes populated, either the row 0, 0 or the row 3, 3 term of the state becomes populated. And so then there becomes a minimum threshold that needs to be overcome in order to get non-zero concurrence. All right, so lastly, we looked at the quantum capacity upper bounds. So our motivation for looking at this is that we wanted to just basically quantify how good a channel is at quantum communication tasks over many uses. And so we thought if we could get some bounds on the capacity, then that would be sort of a probe as to how well this channel can perform those tasks. So just to briefly give a simple definition, the quantum capacity is the maximum number of qubits per channel use that can be transmitted with arbitrarily high fidelity in the limit of many uses of the channel. And the way that we were able to obtain any upper bounds is because we found that you could rewrite the super operator of the nth channel as a product of two super operators that correspond to a generalized amplitude damping channel and a dephasing channel in this way. So it's just simply if we took out the AN terms from the diagonal, and then given this kind of decomposition into products, there's a result that says that then the quantum capacity, which we represent with capital Q of the end-use channel, is less than or equal to the minimum of the quantum capacity of either the generalized amplitude damping channel or the generalized or the dephasing channel. So then, using this result, and known results. So this is powerful because the quantum capacities of both these two channels are known. So then using results on known quantum capacities for transfer times that are again suffering from like the same error at each use, we were able to show that the quantum capacity of the end use is strictly less than or equal to that of the previous use. So with each use, we get a reduction in the quantum capacity of the channel. All right, so now some concluding remarks. So in conclusion, we derive an analytic expression for the end-use average fidelity, and we derive the end-use average dynamical map. We evaluated these expressions considering a perfect state transfer scheme and illustrated how under equal readout timing errors, the average fidelity is only detrimentally affected by memory effects. Using the same scheme, we evaluated the concurrence of transferring 1/2 of a Bell state n times, or 1 part of a Bell state n times, and found timing errors for which the transmitted concurrence is 0, and using a particular decomposition of the end-use dynamical map in terms of the product of GADC and dephasing channels, we saw that under repeated uses with equal readout times, the quantum capacity is strictly non-increasing. Thank you for your attention.
We have tried to generalize to
So non-quadratic? You mean that don't have that aren't quadratic? Yeah. You said that they don't have.
You have the same coupling next.
Yeah. Okay. So then that wouldn't be. That wouldn't have you. Oh, no, we haven't. And we have, there is an expression that holds when the Hamiltonian is only U1. So, yeah. So it wouldn't simplify to something compact, right?
Question.
Thanks.